Okay, thank you, Ron. Thank you, everyone, for coming. So I basically want to try and talk about the VDF project from a holistic perspective. And I kind of think of it as a moonshot in the sense that it's a very valuable thing to try and pursue. It's very difficult and risky, and yet we're compelled to do it, and we have a real shot at succeeding here. So just to make sure we're on the same page, what is a verifiable delay function? Well, the F stands for function in VDF, and what that means is that for every input, you have a unique and well-defined output, so that's pretty easy. The D means that you have some sort of difficulty. So D stands for delay, and the idea here is that you have the sequential computation, as Ron explained, and it's parameterizable, and the second input to the VDF is also called the time parameter. And then, and this is kind of one of the innovations, which is very recent, which kind of separates VDF from time locks a little bit, is that you have, in addition to the output, you have a second output, an auxiliary proof, which basically, after you've done all the computation and you have the output, then there's a very easy way to produce this proof. And this proof is very nice. It's only a few hundred bytes, and it can be verified extremely fast. Okay, so this definition looks pretty simple. What's the big deal? And it turns out there's huge challenges to actually instantiating this new cryptographic primitive in production. So one challenge is that you have, it's a very recent construction. Both the basic primitive was only discovered last year, and also the systems in which they're going to live, the interactions between the existing components are kind of untested. We also have these exotic setups. So the efficient VDFs that we know of require so-called a group of unknown order, and we have RSA groups and we have class groups. RSA groups, require trusted setups or very clever stuff. Or you can use the class groups. So the class groups themselves are very exotic objects in the world of cryptography. So that's a challenge. We also have new cryptographic assumptions, which are very exotic, involving timing. That's kind of a new thing for the world of crypto in a way. The other difficult thing is that we have hardware involved. Usually cryptography is a lot of software, and especially in the world of blockchains, it's lots of software. But here we want to do hardware, and one of the constraints that we have in our space from a cultural standpoint is that we want to do everything open source, and that adds another challenge because hardware is generally all closed source, all NDAs, IP, and all that stuff. So we're kind of fighting against the current here. And for the security of our constructions, it's critical that we have these very fast circuits. And so that adds another challenge. And one of the ideas that we have here is to try and crowdsource the R&D of these ASICs using competitions. But this has never been done before. So we want to have a $1 million circuit competition, but no one's been done before. So we're breaking new ground here. And we also need to look at exotic hardware, exotic optimizations, all sorts of crazy stuff. And also, for VDFs to be successful, we not only need the designers of the system to do their job correctly, and the builders, we also need the community. So in various places, the community, for example, Ethereum community, but also the wider space of blockchains, they need to be active. So one thing they need to do is actually run the VDF hardware in their homes. And ideally, we'd have large decentralization from a large group of people. We're also going to need people to participate in the MPC, so the multi-party computation, so the ceremony to generate this exotic setup. And we're hoping to have 1,000 people with very diverse backgrounds. And the idea is that we only need one single person in these 1,000 people to be honest, and the whole thing is secure. And so we'd like people with misaligned interests to participate. And the final challenge is that when you build hardware, it's really expensive. So we're talking, over $10 million, maybe $15 million, maybe $20 million. And so the strategy that we've taken here is a kind of industry cross-blockchain effort where we have multiple parties kind of chipping in from a funding perspective. And this is still an evolving discussion. Okay, so what are the motivations? Why would we go through all this pain? And one of the initial use cases is randomness. And here we have lots of different projects that want to kind of use VDFs for randomness. And specifically, what VDFs give you is the notion of unbiasable, decentralized, and trustless randomness with the additional great property that it has so-called strong liveness, in the sense that you have a steady production of random numbers, which is very difficult to stop. So even if most people are offline, and in like a catastrophic scenario, you still have the random numbers that are produced. And random numbers are very important to blockchains because it's basically a way of sampling consensus participants to do various tasks. So for example, sampling a block proposer to create a new block. Very similar to what proof of work is. Like proof of work is like, you can think of it as a random beacon, like a random mechanism to fairly sample a block proposer to extend the blockchain. And this mechanism needs to be fair in the sense that the probability of being selected is proportional to the resource at stake. So I want to quickly kind of give you an intuition as to why randomness is related to VDFs, kind of this strange thing. Why is time and randomness connected? So I'll just briefly give you an analogy. So imagine that you have 100 people, and you have a dark room, and the 100 people are invited to come in the room one by one. And in the room, you have a set of dice. And when they come in, they're invited to roll the dice. And they can just go ahead and roll it without, well, they can't see what they're rolling, and then they can just do a random roll. And then once everyone has gone through the room, you turn on the lights, and when you look at the dice, that's going to be a fair random number. And the reason is that if there's even one single honest participant in the 100 people, then the dice will have suffered like a random permutation by this person who bothered to roll the dice. And what VDFs provide is basically they make sure that the lights are not turned on too early. So they provide this kind of minimum guaranteed delay within which whenever you roll the dice, you have the guarantee that it's done in the blind. And that's why we have random numbers. Okay. Other applications involve like new forms of consensus. So consensus is all about taking a scarce resource and then coming to consensus using that. We have proof of work, which uses kind of computation and burning electricity. We have proof of stake, which is based on economic scarce resources. And now we have these new forms of consensus, which are based on like data, like on storage. And we have two flavors. We have the Chia flavor, the Filecoin flavor. And like the interesting thing is that they both use VDFs at their core. So Mariano today will give a talk on the Chia consensus. And then we have all sorts of other applications. So we have proof of history, anti-front running, and I'm expecting a very long tail of applications. So expiring zero-knowledge proofs, time locks, guaranteed output delivery, all sorts of cool stuff. So basically we have this new cryptographic primitive, which is extremely versatile, and it's a building block to build complex systems, especially in the space of blockchains and decentralized systems where you don't want to trust anyone. You can think of it as a cryptographic primitive with the unique property that it has a notion of time. Okay, and in terms of blockchain interest, historically, we've had Chia and Solana, which were kind of the visionaries. They were working with VDFs even before they were invented, working with proto-VDFs. And then once they were discovered recently, Ethereum and Filecoin got involved. And in the last few months, there's been a flurry of interest. Like everyone wants VDFs. So we might be at the peak of the hype bubble, but hopefully not. And hopefully we'll see these in production. Okay, so what has been the progress so far? So these are the three original papers. Bonnet, Bonneau, Bones, and Fish basically defined the notion of a VDF, and they tried to survey the field, and they had these proto-VDFs, and they had an attempt with like SNARKs, recursive SNARKs, but it's really like the two next papers by Wesolowski and Pieczak that kind of gave these wonderful, beautifully simple and efficient constructions. And the amazing thing is that these three papers, which kind of form the genesis of the VDF as a field of study, were all published in June 2018, in the same month, and they were all published within 10 days of each other. So there must have been some coordination. Oh yeah. But yeah, it's amazing that today we're in May. This is like less than a year since the academic discovery of these things. Okay, so what else have we made progress in other than just inventing them? Well, we've made progress on the RSA MPC. So these constructions assume a group of unknown order, and one of the kind of nice ways forward is to try and build an RSA modulus, basically the product of two large primes, in such a way that it's of unknown factorization, so no one knows the two prime factors. And so one way to do that is to have this multi-party computation with lots of people, and you have this so-called n-1 maliciously secure security. So only one single person needs to be honest, and the whole thing is secure. And we want it to be very scalable, 1,000 participants. So these are kind of the constraints. And when we looked in the literature, no one could do this. It was like we were very, very far from being able to do this. Like the constructions were not scalable, or they were not maliciously secure, or like you needed honest majority as opposed to honest minority. It was a big field of research until we met the Mutu and his team from Ligero, and they were like, yeah, we can. It's hard, but we can do this. I have a good intuition for it. Okay, yeah, I'll add the university. Like we've been doing some recent stuff. There's been some recent breakthroughs. Maybe we can pull it off. And here we are today, and these are kind of like the cost that we have to pay for the MPC. So, like it's kind of like a fundamental constraint that the MPC be synchronous. So that's a high cost in the sense that everyone needs to be online at the same point in time in order to participate in this MPC. But the good news is that the communication complexity is very manageable, even for 1,000 participants, and even for a large modulus that's 2,000 bits. So less than 100 megabytes per participant of communication, 5 to 10 rounds of communication. So every round is very, minimizing the number of rounds is important because you have to wait for all 1,000 people to have completed the round in order to move to the next round. And so hopefully we'll be able to get this thing done in a few minutes. And I guess the plan right now is to do the real MPC production one next year, once we've gone through all the testing and the logistics and, very importantly, all the security audits. Okay, what is the other big challenge? So the other big challenge is to build hardware that's really, really fast, and the security of our systems depend on it. Now, one important thing to realize is that we don't need to be the fastest hardware in the world. We just need to be not too slow. And specifically, we need to be within a constant factor of what an attacker can do. And this constant could be, generally it's like a parameter that can be set in your protocol. So you can set it to 10 or 100. So in other words, you need to make sure that no attacker can be 10 or 100 times faster than what you can do. And so, one of the breakthroughs, and Erdinch will be giving a talk on this, is that we have a new low-depth algorithm for the modular multiplication, which is the basic sequential step. And it's the lowest depth that I know of modular multiplication. And we have a supranational that have basically implemented this algorithm in FPGA, and I believe as far as I can tell, they have the fastest implementation at 66 nanoseconds, and that was used to as a proof of concept to crack the LCS35, and that was done in collaboration with Amazon, who provided the hardware. Okay, so that's what's been done so far. Lots of progress, mostly with two teams, one on the hardware side, one on the MPC side. And now what are the next steps? So a lot of the next steps involve the community. So one of the things we want to do is these competitions. We want to do at least two competitions, one FPGA competition and one ASIC competition. The FPGA competition would be a kind of a warm-up competition with a $100,000 prize. And we want to try and reduce the latency, ideally something like 30 nanoseconds or less. And we're looking to do that next year, and we'd use the AWS infrastructure. And just to give you orders of magnitude, the current hardware using CPUs performs a single modular multiplication in 900 nanoseconds. So 66 nanoseconds is a huge speed up, and 30 nanoseconds is like a 30x speed up. And then after the competition, next year, we're looking to do this $1 million competition, and we're hoping to go at 1 nanosecond or less. And so the rough orders of magnitude is that FPGAs are roughly 30 times faster than FPGAs are roughly 30 times faster than CPUs, and ASICs roughly 30 times faster than FPGAs. Okay, and there's also the MPC, as I mentioned. So we want to have these very diverse set of participants. Hopefully we'll have like whistleblowers and cryptographers and hardware people and all sorts of people who don't necessarily know each other, and they couldn't all coordinate and maliciously kind of undermine the system. And so one of the details here is that we're going to have a coordinator to help facilitate the communication between all these participants. But the good news is that the coordinator is trustless. So the security of the system is not compromised if the coordinator is malicious. Instead, the coordinator is just there to facilitate the networking. And we're looking to use AWS or Cloudflare as the coordinator. Okay, and then there's the hardware distribution aspect, where we want at least one VDF rig to be online. That's kind of the requirement for Ethereum randomness. It's like this maximally minimal requirement. You just need one single person in the whole world to run this, the hardware. But just for simplicity of the protocol, we're not giving away rewards in the protocol. So usually, what we do in the blockchain space to incentivize people is just to give them a reward, and that's the easy way out. But here it adds significant complexity. So instead, what we're going to do is we're going to build these ASICs and give them away for free to the community, which itself is a crazy idea. I don't think it's ever been done at that scale. Like thousands of VDF rigs, send them around the world, and just give them to a very diverse set of people, enthusiasts, investors, academics, journalists, whatever, museums, whoever will run it. And maybe we might even put one on a satellite. That would be amazing. And yeah, that's the hardware distribution aspect. And then the final point where we need community involvement is the finances. So as I said, it's a very expensive project. And right now, the current sponsors are protocol labs, like the foundation behind Filecoin, and the Ethereum Foundation, which is the foundation behind Ethereum. And right now, we split the development cost 50-50, but we want more people to get involved. We need more people to get involved, and we're in discussions with various projects in terms of funding. And one way where we can kind of align the incentives on this public good, generally funding public good things is difficult, but here we might have an interesting approach, which is that in a VDF rig, we can have more than one ASIC. We could have 20, 30, 50 ASICs. And so a single rig can support the network of multiple blockchain projects. And so what we could do is basically allow all the blockchain projects to benefit from all the decentralization of all the other blockchain projects. So it's kind of a win-win situation. And we could potentially sell kind of slots on the VDF rig in terms of default configuration. So by default, if you receive a VDF rig, you'll be supporting these projects. Okay, research. So there's still a bunch of open problems to be solved, and part of the idea of meeting today is to try and start tackling these problems. This is the third VDF day, and in the previous two, we made lots of progress. So if you're interested in like catching up with the research, if you're kind of new, there's this great resource called vdfresearch.org, which gives you like links to all the papers, lots of educational material like videos and tutorials to get up to speed. Okay, so these are some of the incremental improvements to the basic cryptographic primitives that we've made, during VDF Day 1 and VDF Day 2, and also a bit recently. So in proofs, we found ways to aggregate proofs, and that actually unlocks the possibility to do incremental VDFs. We also found a way to reduce the proof size to just one single RSA element. So if you have an RSA group of 2,000 bits, then the proof size is just 2,000 bits, which is 256 bytes, tiny. We found new and improved provers. So we have the iterated Wysocki prover, which is much more efficient than the plain Wysocki. We've had hybrids where we mix, Pieczak and Wysocki, which has so we're basically exploring the set of trade-offs, and we're finding like the best constructions appropriate for us. And we also made like some recent like mini breakthroughs in time locks. So like the construction by Ron requires like a programmable modulus, where the time lock creator chooses his modulus, he knows the factorization. But this is not necessarily a luxury that you have with a fixed modulus in hardware. So we're looking to fix the modulus. And it's also a luxury that you don't have with class groups. So class groups is a group of a known order, but I don't know of any way to kind of cheat and know the order of the group. And so it turns out there's a very small tweak you can do to the time lock scheme so that basically the secret, instead of being encoded in the factorization of the modulus, you encode it in the input. So the input in Ron's scheme is 2, and that's fine. But if you just use a different input, then you can have a time lock with a fixed modulus or with class group. There's been also various other discoveries recently, like blinded time locks and time lock pub keys, which is kind of nice. And there's also new constructions from the world of academia. So there's a recent one based on isogenies and pairings. They were trying to build a quantum secure VDF, and so they went down the route of isogenies. Turned out that they didn't quite succeed because of the pairings, but it's still very interesting. And I think there might be a talk today on yet another construction. Okay, so this is the schedule for today. We have talks in the morning, then we have lunch, and then we have these workshops where hopefully we'll make progress on the open problems. And then we can take a bit of time to debrief and share the learnings. And then there will be kind of an optional dinner. I should have removed this from the slides. Basically, there's only 20 seats, but it looks like we might actually be okay. Yeah, and I wanted to thank our host here today, MIT CCEL and the MIT Digital Currency Initiative. This is a great venue, great people. Even before VDF Day, a lot of progress were made just by knocking on doors of like complexity theorists and talking to them about open problems. It's just amazing that there's all these smart people in one place. So these are the workshops. There's going to be like a theme per workshop. So MPC, alternative constructions, applications of VDFs, fast hardware, and the circuit lower bounds. And each workshop has a lead. Yeah, I'll make sure to share open problems for each of these themes in the afternoon. OK, thank you.